Airbus A320 aircraft performance including GRF. Objective: to ensure pilot will develop a comprehensive understanding of aircraft performance, takeoff, climb, cruise, descent, and landing. Demonstrate proficiency in using global reporting format to assess runway conditions. Apply braking action reports and contamination data to adjust performance computations.
Definition and purpose. Definition: Airbus, Getting to Grips with Aircraft Performance, Chapter 1. The capability of an aircraft to safely achieve specific flight phases under defined conditions, meeting CS-25 and FAR-25 requirements. Performance is measured, demonstrated in flight tests, and recorded in the AFM. Purpose in airline operations, FCOM Intro. Ensure safe operation within certified limits. Optimize payload, range, and fuel efficiency. Provide accurate data for dispatch and in-flight decision-making.
Performance components and phases. Takeoff performance, fill length, V-speeds, climb gradient. Climb performance, all engines operating, AEO, and one engine inoperative, OEI. Cruise performance, optimum altitude, speed schedules. Descent performance, rate, path management, energy control. Landing performance, landing distance required, LDR under various conditions.
Factors affecting takeoff performance. Aircraft weight. Increase takeoff weight or landing weight, longer field lengths, reduce climb gradient. Center of gravity. Forward CG, increase drag. Aft CG, reduce stability. Environmental conditions. Wind. Headwind improves, tailwind degrades performance. Temperature. High OAT, reduce thrust and lift. Pressure altitude. High altitude reduces air density. Regulatory framework. Getting to Grips with Aircraft Performance, Chapter 3. Hierarchy. ICAO SARPS, Annex 6 and 14, Global Standards. EASA/FAA, Certification and Operational Rules. CS-25/FAR-25, Detailed Performance Requirements. Certification versus operational. Certification, minimum safety standards in control test conditions. Operational, additional margins, example, LDA times 1.15 in flight for airline use. CS-25 versus FAR-25, structure of limitations, common structure. Takeoff performance requirements. Climb radiant requirements, AEO and OEI. En route OEI drift down. Landing performance. Differences? Minor wording or procedural differences. Airbus data meets both.
Airbus documentation flow, GTG Chapter 4, and FCOM Intro. FAM, Aircraft Flight Manual. Legally binding, contains certified data and limitations. FCOM, Flight Crew Operating Manual. Based on FAM data, adapted for operational use. Contains performance tables, QRH cross-references, MEL, CDL adjustments. Relationship. ICAO through EASA, through FAA, through CS-25, through FAM, through FCOM, through flight crew. Summary and key takeaways. Performance knowledge is essential for safe, efficient, and compliant operations. Always consider weight, CG, and environment in performance calculations. Regulatory chain ensures data integrity from ICAO standards to cockpit tables. AFM is certified truth. FCOM is operational application. This foundation applies to all subsequent topics: takeoff, climb, cruise, descent, and landing.
Takeoff performance.
Scope and objectives. Purpose: ensure safe airborne transition and required climb gradient compliance under given conditions. Regulatory basis: CS-25, FAR-25, accelerate stop, accelerate go, obstacle clearance requirements. Performance data sources: AFM, certified data; FCOM, operational application for pilots. Flight phases covered: ground roll, rotation, liftoff, climb segments.
Regulatory requirements. Certification standards for takeoff. CS25/FAR25 key points. Balanced field length determination. OEI climb gradient minima. V-speed definitions and criteria. Demonstration with worn brakes for VMBE. ICAO link. Annex 6, Operational Performance Rules. V-speeds. Limiting speeds. VS, VS1G, VSR, VMCG, VMCA, VMU, VMBE, V-tire. Operating speeds: V1, VF, VR, V liftoff, V2, V operations, F speed, S speed, green dot speed, VFE, VLE, VLS.
Key V speeds. Part 1. Essential speeds for takeoff. V1, decision speed to continue or abort takeoff. VR, rotation speed, initiate nose-up pitch. V2, takeoff safety speed after engine failure. Calculation factors: weight, flap setting, environmental conditions. Key V speeds. Part 2. VMBE, maximum brake energy speed, braking capability in rejected takeoff. VMU, minimum unsticking speed, lowest safe liftoff without tail or wing strike. VMCG, minimum control speed on the ground with one engine inoperative. VMCA, minimum control speed airborne, maintain straight flight with one engine inoperative.
Key V speeds, Part 3. V-tire, maximum tire speed. The tire manufacturer specifies the maximum ground speed in order to limit the centrifugal forces and the heat generation that may damage the tire structure. Note: for example, for A321 XLR aircraft, V-tire equals 235 miles per hour, published as 204 knots in Airbus documentation.
Balanced field length. Accelerate stop versus accelerate go. Accelerate stop, distance to reach V1 and stop safely. Accelerate go, distance to reach V1, lose an engine, and continue to liftoff. Balanced field length, both distances equal, determines maximum takeoff weight for given conditions. Impact factors, weight, thrust, and environmental conditions. Factors affecting takeoff performance. Primary influences. Aircraft weight. Heavier, longer ground roll, reduced climb gradient. Environmental. Pressure altitude. Temperature, ISA deviation. Wind. Slope. Surface condition. Configuration. Flaps, slat setting. Thrust rating. toga, flex, or derate. Flex and derate operations. Flex is an assumed temperature method of reducing thrust while meeting performance margins. Derate is a fixed lower thrust setting. If installed, can combine with flex. The benefits include saving the engine life, improve engine reliability, and reduce maintenance costs. The limitations are not allowed on contaminated runways and must meet the OEI climb. Flexible takeoff. Thrust level less than toga. Performance computation by adjusting the max takeoff thrust performance. Use of a single takeoff chart calculated for toga. Possibility to recover toga at any moment. Not allowed on contaminated runways. No performance improvement. Derated takeoff. Thrust level less than toga. New set of performance data provided in the flight manual for each derate level. Use of a specific takeoff chart for each derate level. Toga selection not possible. Allowed on contaminated runways. Increase of takeoff weight on short and contaminated runways VMCG limited. Engine thrust limitation. 5-minute toga thrust with all engines operating. 10-minute toga thrust with one engine inoperative. 2 different goals during one engine inoperative and all engines operating. One engine inoperative. Safety. Respecting official requirements. Operating rules. Airworthiness. All engines operating. Operational. Respecting airport constraints. Engine failure considerations. One engine inoperative during takeoff. Certification. Must demonstrate safe continuation after OEI at V1. Takeoff segments. First segment, since liftoff to gear retraction. Second segment, gear up to acceleration altitude. Acceleration segment, accelerate to final climb speed. Final segment, climb to en route altitude. Operational notes. Adjust thrust, maintain control, follow SID or engine out procedures.
Takeoff on wet runways. Wet runway performance. Definition: water less than 3 millimeters depth on greater than or equal to 25% of surface. Impact: reduced acceleration, longer takeoff roll. Adjustments: use wet runway performance tables. Consider full thrust if margins are small. Wind benefit: headwind can partially offset wet penalty. Takeoff on contaminated runways. Contaminated runway considerations. Definition: greater than 25% surface covered by greater than 3 millimeters water, slush, snow, or ice. Impact: significant acceleration reduction, longer takeoff distance. Operational actions: use toga thrust. Apply specific contaminated runway data from AFM or FCOM. Review OEI procedure for reduced directional control. Consider GRF or RCAM runway reports.
Takeoff using GRF. Global Reporting Format Introduction. Implemented globally from 4 November 2021 by ICAO. Standardized method of runway condition assessment and reporting. Enhances communication between airport operators, ATC, and flight crews. Core output. Runway condition report with RWYCC or Runway Condition Code. GRF objectives and benefits. Harmonized assessment for all airports. Links observed runway conditions with performance data and aircraft manuals. Supports safer takeoff and landing decision-making. Reduces ambiguity from subjective terms like slippery and wet into coded values.
Runway Condition Report, or RCR. Components: aerodrome location indicator and date and time, runway designator, RWYCC for each third of runway, touchdown, mid, rollout. Surface description: example, wet, compacted snow or ice. Depth of contaminant, if applicable. Temperature, percentage coverage. Pilot reported braking action, if available.
Runway Condition Codes, or RWCC. The scale is 0 to 6. 6 is dry, 5 is good, wet up to 3 millimeters, 4 is good to medium, 3 is medium, 2 is medium to poor, 1 is poor, and 0 is nil, or no braking action. RWCC is derived from RCAM table based on observed conditions. The Runway Condition Assessment Matrix, RCAM, maps surface type, contaminant depth, and temperature to RWYCC. Examples: dry, 6. Wet, greater than 25% coverage, less than 3 millimeters, 5. Slush or water, greater than 3 millimeters, less than 3 degrees Celsius, is 2 or 1. Operators use RWYCC to determine takeoff and landing performance penalty from AFM or FCOM tables.
Contaminated runway surface condition. 1. Standing water. Water more than 3 millimeters deep, including running water of this depth. 2. Dry snow. Snow too dry to form a snowball. Snow from which a snowball cannot readily be made. 3. Wet snow. Snow that contains enough water content to be able to make a well-compacted solid snowball, but water will not squeeze out. 4. Slush. Snow that is so water-saturated that water will drain from it when a handful is picked up or will splatter if stepped on forcefully. 5. Compacted snow. Snow that has been compacted into a solid mass such that aeroplane tires at operating pressures and loadings will run on the surface without significant further compaction or rutting of the surface. 6. Frost. Frost is a thin layer of ice crystals formed when moisture freezes on a cold surface. Unlike solid ice, frost has a grainy texture. It can make the runway slippery and is reported as reduced braking action. 7. Ice. Water that has frozen or compacted snow that has transitioned into ice in cold and dry conditions. 8. Wet ice. Wet ice is ice with water on top or melting ice. It makes the runway extremely slippery, often leading to reduced braking action reports in line with ICAO procedures.
Applying GRF to takeoff performance. Process. Obtain latest RCR from ATC or dispatch. Identify lowest RWICC affecting takeoff roll. Refer to A320 FCOM contaminated runway takeoff tables. Apply corresponding performance adjustments. Increased takeoff distance.
EFB, Wet and Contaminated Runway Takeoff. Open EFB, Performance Module. Select Airport and Runway. Input Runway Condition, RWCC. Contaminant type, wet, slush, snow, ice, depth or coverage. Select A320 variant and config, flaps, anti-ice. Low RWCC, EFB may suggest TOGA. EFB calculates TODA, V-speeds, maximum takeoff weight. Cross-check with FCOM wet and contaminated tables. Confirm values, set in FMGS, monitor acceleration.
MEL-CDL considerations. MEL items, e.g. inoperative anti-skid, may require RWICC downgrade or prohibit operations. CDL items, missing gear doors, fairings, can increase drag, further reducing performance. Must combine MEL-CDL penalties with GRF adjustments before final performance calculation.
RWCC adjustments and limitations. Pilot reports can upgrade or downgrade RWCC based on actual braking action. Temperature changes may improve or deteriorate surface friction rapidly. Contaminant removal. If significant clearance, reassess RWCC. Limitations. RWCC applies to performance, not necessarily to controllability. Additional margin may be required. Takeoff may be prohibited at RWCC 0 without mitigation.
Limitations. From Thai Air Asia OP, Part A. The first officer are not permitted to take off and landing on contaminated or slippery runway.
Limitations. From Thai Air Asia OM, Part A. The first officer is not permitted to take off and landing on a contaminated or slippery runway. Takeoff and landing are not allowed when the reported braking action is poor or when the reported braking friction coefficient is equal to or less than 0.25, RWCC less than 2.
Climb performance. Climb performance overview. Purpose: ensures safe clearance from obstacles, efficient transition to cruise. Two main cases. All engines operating, AEO, higher climb gradients used for normal operations. One engine inoperative, OEI, lower gradients, critical for regulatory compliance. Governed by CS25/FAR25 certification standard. All engine operations versus one engine inoperative climb gradient. All engines operations climb gradient. Normally well above minimum required by regulations. Limited by thrust setting, temperature, weight. One engine inoperative climb gradient. Determined after engine failure at critical point. Must meet minimum regulatory gradient for obstacle clearance. Formula: rate of climb divided by ground speed times 100. Net versus gross climb gradient. Gross gradient, flight test result under ideal conditions by test pilots. Net gradient, gross minus safety margin to account for operational variability. AEO, gross minus 0.8%, OEI, gross minus 0.8 to 1.1% depending on segment. Regulatory use, obstacle clearance planning always uses net gradient. Takeoff segments. Overview. 4 distinct segments in the OEI takeoff climb. First segment, liftoff to gear retraction. Second segment, gear up to acceleration altitude. Acceleration segment, level or low climb while accelerating to final climb speed. And final segment, steady climb to en route altitude. Each segment has specific minimum gradient requirements. First segment, OEI, liftoff, to landing gear fully retracted. Characteristics: high drag due to gear down, low climb gradient. Requirement: positive climb gradient required. Second segment, OEI, gear fully retracted. This segment begins upon gear retraction and continues until the first full segment climb gradient, which is reached at acceleration altitude, typically 400 to 1500 feet AGL. Requirement for A320 twin is G greater than equal to 2.4% net climb gradient, most demanding segment for performance calculations. Acceleration segment. At acceleration altitude after second segment. Action. Level off or shallow climb to accelerate to final takeoff climb speed. Requirement. No specific gradient but must maintain obstacle clearance. At final climb speed after acceleration. Minimum 1,500 feet above airfield or en route altitude. Requirement for A320 twin greater than or equal to 1.2% net climb gradient. Obstacle clearance. Regulation. Must clear all obstacles by at least 35 feet at the end of takeoff distance. Net gradient used to assess against departure paths and obstacle databases. Critical for OEI. Determines MTW for given runway and conditions. Maximum climb thrust and OEI considerations. Maximum climb thrust, or climb schedule, is managed via thrust reduction and speed schedule for efficiency and engine life. OEI drift down. Controlled descent from cruise when aircraft cannot maintain altitude with one engine. Engine out maximum altitude. Maximum OEI altitude based on weight, ISA deviation, and configuration. Mountainous terrain. Pre-planned escape routes and drift down profiles.
Cruise performance. Cruise performance overview. Purpose: achieve most efficient fuel time trade-off while maintaining operational constraints. Cruise types: Econ, long-range cruise, LRC, fixed Mach, speed, max range. Balances cost index, winds, fuel, and ATC constraints.
Cruise speeds. There are two ways to operate the aircraft in cruise: by the direct selection of the speed by the crew, selected speed, by the use of optimum speed computed by the FMS based on the cost index, CI, managed speed. Refer to the chapter Cruise at Minimum Cost.
Managed speed. A flight guidance mode is managed when the FG manages the aircraft along the FMS F plan, e.g., nav mode. A speed target is managed when the speed value is computed by the FMS, e.g., Econ. The selected speed is a flight guidance mode, and its associated target is selected when the flight guidance manages the aircraft to a target selected by the pilot on the AFS-CP, for example, heading. A speed target is selected when directly selected by the pilot on the AFS-CP. The speed target is used by the autopilot FD and by the auto thrust as a target. Econ cruise. Definition: speed-altitude combination optimized for cost index. Cost index balances time-related cost, crew, maintenance, with fuel cost. Higher cost index, higher cruise speed, more fuel burn, less time. Lower cost index, lower speed, less fuel burn, more time. Long-range cruise, or LRC, is the speed giving 99% of max range with slightly higher speed. Slightly higher fuel burn than max range speed, but better operational flexibility. Used when schedule adherence is less critical and fuel economy is priority. Fixed Mach cruise or speed. Maintain constant Mach number regardless of cost index optimization. Common for ATC flow requirements or mixed fleet operations. Less efficient than Econ long-range cruise when winds or temperatures vary significantly. Maximum range cruise. Definition: speed yielding absolute minimum fuel per distance. Typically slower than long-range cruise, rarely used in airline operations due to increased block time. Can be useful in extended diversion or fuel-critical scenarios. The soft altitude mode minimizes thrust variations. 2 minutes after reaching the planned cruise altitude, soft altitude mode engages. This allows the aircraft to deviate plus or minus 50 feet in order to maintain the cruise Mach, thereby minimizing thrust variations and reducing fuel consumption. Maximum recommended altitude, FMS computation. The maximum recommended altitude is the lowest of climb ceiling, maximum cruise altitude, maximum certified altitude, 1.3 G buffet limited altitude. Optimum altitude. Definition: altitude giving lowest fuel burn for given weight and temperature. Increases as weight decreases during flight. Determined from FCOM performance tables or FMC predictions. At high altitudes, watch for buffet margin and engine thrust limits. Step climb procedures. Used to follow optimum altitude as weight reduces. FMC suggests step climbs, e.g. 2,000 feet increments, to stay near optimum altitude. Benefits: reduced fuel burn, increased range. Constraints: ATC clearance, terrain, and turbulence. Wind effect on cruise. Headwind favors higher speeds to minimize exposure time. Tailwind favors slower speeds to maximize wind benefit. Wind component critical in cost index or econ calculations. Large wind gradients with altitude can change optimum altitude selection. Fuel burn implications. Higher altitude, lower fuel flow, but reduced thrust margin. Speed selection affects drag profile, parasite drag versus induced drag. Step climbs and correct cost index settings can save significant fuel over long sectors. Fuel savings from cruise optimization often exceed takeoff and climb optimization gains. Cruise performance limitations. Weight limits. Maximum cruise altitude constrained by thrust and buffet margins. Temperature. High ISA deviation reduces climb capability and may limit cruise altitude. Turbulence penetration. May require lower Mach altitude. ATC constraints. Can force suboptimal altitude speed. Engine out cruise. Reduced altitude and speed, drift down profile applies.
Descent performance. Descent performance overview. Objective: manage descent profile for efficiency, safety, and ATC compliance. Includes speed, thrust setting, and altitude change planning. Key factors: airspace constraints, fuel economy, and energy state. Types of descent. Normal descent. Planned, managed descent using FMC, VNAV, and LNAV guidance. Idle descent, open descent. Thrust levers at idle for most of descent maximizes fuel efficiency. Emergency descent. Rapid altitude loss in response to pressurization or other emergencies. Normal descent profile. Managed via FMS with descent path calculated from top of descent. Balances rate of descent and speed to meet crossing restrictions. Often uses econ speed for fuel time balance. Continuous descent operations are preferred for efficiency and noise reduction. Managed descent mode. The managed descent mode guides the aircraft along the FMS-computed vertical flight path.
The DES mode is preferred when conditions permit since it ensures the management of altitude constraints and reduces the operating cost when flying at econ-des speed. The DES mode is only available when the aircraft flies on the FMS lateral flight plan, that is to say, when the aircraft uses the nav horizontal guidance mode.
Idle descent is managed via FMS with descent path calculated from top of descent, balances rate of descent and speed to meet crossing restrictions, often uses econ speed for fuel time balance, continuous descent operations preferred for efficiency and noise reduction.
Selected descent, open descent and vert speed. In open descent mode, the AFS commands idle thrust and the elevators adjust the pitch to maintain the target speed, managed or selected. The open descent mode can be used to increase or reduce the descent slope. In open descent, the flight crew adjusts the target speed to modify the descent path. More selected speed increase equals more descent slope increase. Emergency descent. Triggered by rapid depressurization, smoke, or other urgent threats. Goal: reach safe, breathable altitude, e.g., 10,000 feet, as quickly as possible. Typical profile: thrust idle, speed brakes full, descent rate greater than 6,000 feet per minute. Controlled to avoid overspeed and structural limits. Descent rate and angle. Descent rate, feet per minute, is controlled by pitch attitude and thrust. Descent angle is determined by energy state. Typical managed descent, 3 degrees. Steeper descents increase rate but require more drag or reduced speed. Wind affects ground track angle. Balance between potential energy, altitude, and kinetic energy, speed. Avoid excessive speed requiring speed brake use. Plan top of descent to minimize level-off segments. Early descent wastes potential energy. Late descent risks high rates and unstabilized approach. Descent planning factors. Weight. Heavier aircraft descend faster at higher speeds. Winds. Strong tailwind increases ground speed, reduces descent time. ATC constraints. Crossing altitudes, holding patterns. Weather. Turbulence or icing may limit descent profile. Impact of the wind on the descent path. The descent path computed by the FMS uses the forecasted wind entered in the descent wind page. However, in flight, actual conditions may vary from the predicted ones. As a consequence, the difference between the predicted descent wind and the actual wind, delta wind, affects the aircraft's behavior. If the speed target is maintained, as in open descent mode, the aircraft tends to leave the FMS computed idle path. Holding performance considerations. Holding consumes more fuel at lower altitudes due to higher thrust settings. Higher holds are more fuel efficient, but may not be possible due to ATC or weather. Plan holding speeds, such as green dot for fuel economy. Anticipate and load holding pattern in FMS for accurate fuel prediction. Summary and best practices. Use managed idle descent when possible for fuel time efficiency. Monitor descent profile early to avoid last-minute adjustments. Keep ATC informed for profile optimization. Emergency descent procedures must be memorized and practiced. Efficient descent planning saves more fuel over time than small climb improvements.
Landing performance. Landing performance overview. Landing performance is critical for safe runway operations, determined by aircraft speed, weight, configuration, environmental factors, and runway condition. Regulatory basis. CS 25, FAR 25,
certified landing distance plus operational safety margins. Limiting speed, VMCL, minimum control speed for landing. Determination of VMCL, most critical configuration for approach and landing. Aircraft trimmed for AEO approach and landing. Most unfavorable center of gravity. Most unfavorable weight, should speeds be independent from weight. The control of the aircraft must not require exceptional piloting skill, alertness, or strength. Rudder force under 150 lfb, no excessive lateral control force.
Key speeds in landing. Operating speed, VLS. Lowest selectable speed, config 3 or config full. During flight phases, pilots should not select a speed below VLS. Rule applied for landing. During landing, pilots have to maintain a calibrated speed of no less than VLS down to a height of 50 feet above the airport. Operating speed, VREF. Reference speed, VLS config full. Minimum landing speed in landing configuration full at a height of 50 feet above the runway surface. Operating speed of V approach. Final approach speed. During approach phase, flaps and slats in landing configuration, landing gears are extended. VLS, V approach, is greater than or equal to VLS. Correction with headwind, autothrust use, and/or ice accretion to become V approach. Operating speed, V approach. Final approach speed, the FMGS and managed speed is used to define V approach target. It gives efficient effect guidance with windy conditions. V approach target equals ground speed mini plus actual headwind. Ground speed mini equals V approach target minus tower wind. Actual wind is measured by ADIRIS, and the tower wind is entered on the MCDU. Operating speed, V approach. Example, VLS equals 130 knots. Auto thrust on. Tower wind equals 20 knots. V approach equals 130 plus corrections. Maximum 5 and 1/3 tower wind. V approach equals 137 knots. Ground speed mini equals V approach minus tower wind. Ground speed mini equals 117 knots. From the picture, what is the V approach target? Case 1. V approach target equals 137 knots. Case 2. V approach target equals 157 knots. Case 3. V approach target equals 137 V approach minimum value. Operating speed. Green dot speed is the best lift-to-drag ratio speed in the clean configuration. VLS is the lowest selectable speed and provides an appropriate margin to the stall speed. The autopilot will not go below this speed if autothrust is active. Selected speed in the FCU. Alpha prot limit. This speed is maintained when side stick is neutral. If side stick is deflected aft, this will eventually activate alpha floor auto thrust protection. See alpha floor protection. Alpha max is the speed with the maximum angle of attack the aircraft will allow. This speed is maintained when side stick is deflected fully aft. It has a small margin before reaching the stall AOA.
Performance factors. Aircraft weight. Maximum landing weight limits structural loads on landing gear and brakes. Heavier weight, higher V approach, longer landing distance. Dispatch planning must ensure landing weight within maximum landing weight for destination and alternate. Performance factors. Configuration. Flaps and slats. Full landing configuration reduces V approach and landing distance. Partial flap landings require higher speed, which leads to longer distance. Spoilers and auto brake selection affect stopping capability. Environmental factors. Wind. Headwind reduces ground speed, shorter landing distance. Tailwind increases it. Runway slope. Downhill increases landing roll, uphill decreases it. Surface. Contamination. Wet, snow, ice increases stopping distance significantly. Go-around. Go-around requirements. Certified go-around gradients. Operational requirements. Factors of influence. Engine thrust limitation. 5-minute to toga thrust with all engines operating, AEO. 10-minute toga thrust with one engine inoperative, OEI. Go-around requirements. Approach climb gradient limitation. Go-around requirements. Go-around limiting weights. Example. Weight limited by approach go-around requirements in the following conditions. Config 3, airport at sea level, 20 degrees Celsius. Go-around requirements. Landing climb gradient limitation. Minimum gradient 3.2%. Go-around requirements. Go-around limiting weights. The approach climb gradient requirements imply restrictions for landing weight. Tables of go-around limiting weights are in the FCOM. Go-around limiting weights. The landing climb gradient requirement is less limiting than approach climb gradient requirement. Table of landing climb limiting weights is not provided in operational documentation. Missed approach. One engine inoperative. Non-precision and Cat 1 approaches. For instrument approaches with a missed approach climb gradient greater than 2.5%, the operator should verify that the expected landing mass of the aeroplane allows for a missed approach with a climb gradient equal to or greater than the applicable missed approach gradient in the OEI missed approach configuration and at the associated speed. Cat 2 or Cat 3 approach. For instrument approaches with DH below 200 feet, the operator should verify that the expected landing mass of the aeroplane allows a missed approach gradient of climb with the critical engine failed and with the speed and configuration used for a missed approach of at least 2.5%, or the published gradient, whichever is greater. The gradient is 2.5% or more if the approach charts require a higher value for obstacle consideration. What does published missed approach gradient correspond to? PANZOPS IKO Doc 8168 makes standards and recommendations to construct missed approach procedures. PANZOPS assumes normal operations, i.e., all engines operative. Go-around requirements. First segment OEI. Missed approach procedures shall be established for each instrument approach. Shall specify a point where the procedure begins and a point where it ends. Shall terminate at an altitude height sufficient to permit initiation of another approach or return to a designated holding pattern or resumption of en route flight. Ensure acceptable clearance above obstacles during the go-around phase. Account for ATC constraints. Account for airspace restriction. Go-around requirements. PANS OPS. Missed approach procedure design is initiated at the decision altitude decision height in precision approach, the missed approach point in non-precision approach.
Go-around requirements, PANS ops, missed approach procedure design, procedure based on a minimum approach gradient of 2.5%. Start of climb, or SOC, is the reference for calculations of distances and gradients in obstacle clearance. The go-around requirements, PANS ops, missed approach gradient. Start of climb, SOC, is not published. The aircraft must clear published gradient from point when the aircraft has a positive climb gradient to the MAA. Go-around requirements, PANS ops, missed approach, protection area. Depend on the type of departure, straight, turning. Depend on the type of approach. Depend on the navigational aids. Go-around requirements, PANS ops. Examples of missed approach gradient, Bogota, 1-3 left. Go-around climb gradient equals average gradient. Go-around requirements. Examples of missed approach gradient, Bogota, 1-3 left. Go-around requirements. Landing weight may be limited due to green dot reached before 10 men toga and or very high missed approach altitude or gradient. Accelerate at an intermediate altitude. The go-around requirements. Required landing distance, dry. Based on performance charts for dry runway, max landing weight, and standard conditions. CS25/FAR25, certified distance times operational factor, typically times 1.67 for dry. Adjust for headwind, tailwind, slope, temperature. Dispatch versus in-flight landing distance. Dispatch. Pre-flight calculation using regulatory safety factors. In-flight. Updated using actual landing weight, weather, runway conditions. In-flight data, FMS or QRH, often allows lower safety factor, for example, times 1.15 for dry. System failures and performance impact. Brake failure. Reduces deceleration, may exceed available runway length. Thrust reverser inoperative. Increased stopping distance, especially on contaminated runway. Anti-skid failure. Reduces braking efficiency and directional control. Landing distance cross-check. Cross-check FMS predicted landing distance with QRH plus performance app. Verify against runway available length and condition codes. Essential before committing to approach, especially in marginal conditions. Obtain weather 30 minutes before touchdown. Summary. Best practices. Monitor actual landing distance capability before approach. Select landing configuration and auto brake to match runway length and surface. Factor in wind, slope, contamination, and failures. Always perform independent cross-check before landing commitment.
Landing performance using GRF.
Purpose of GRF in landing performance. Apply runway surface condition, RWCC, to adjust landing performance. Use consistent data from ATIS or PIREP or RCR to calculate landing distance required, LDR. Ensure safe stopping within available runway length. Braking action reports landing focus. PIREP's good, medium, poor, or nil specific to landing rollout. ATIS broadcast RWCC and surface description. Cross-check ATIS PIREP before committing to approach.
RWCC downgrade or upgrade in landing context. Downgrade if braking less effective than RWCC suggests. Upgrade only with strong supporting evidence and friction data.
Direct impact on LDR and landing configuration selection. Airbus RCAM landing application. Airbus Performance App/QRH integrates RWCC into LDR tables. Inputs RWCC, slope, wind, weight, flap setting, auto brake reverser status. Outputs LDR adjusted for contamination. Landing distance factors, or LDFs. Dry times 1.15 in flight. Wet times 1.92 dispatch typical. Contaminated RWCC and contamination-specific factor from RCAM, applied after base dry performance from FCOM. Failure considerations with GRF. Thrust reverser in-op higher LDF. Brake or anti-skid failure significantly longer LDR. Must be applied on top of RWCC correction. Cross-check procedures. Compare FMS LDR with QRH or Performance App result. Adjust for runway slope, wind, MEL/CDL items. Abort approach if calculated LDR exceeds runway available. The crew best practices for landing on contaminated runways. Use maximum reverse thrust when safe. Choose higher flap setting for lower approach speed. Ensure auto brake setting matches required deceleration. Summary key landing GRF takeaways. RWCC directly influences LDR. Always use latest values. Downgrade if braking action worse than expected. Always cross-check before approach commitment. Report braking action to support GRF updates for following traffic.
Thank you for your attention.